So we have learned Snell's law and the concept of refractive index. In this session, we'll talk about mirage and real depth versus apparent depth and total internal reflection and the concept of critical angle. Mirage is a phenomenon where you feel there is some water at some distance, but when you go there, there's no water. It typically happens when it is very hot. So this is a picture where you feel there is some water over here, but actually that is just a reflection. For example, the reflection of this peak is here, the reflection of the sky is here, and because of that reflection, we are accustomed to believe that that reflection is happening due to some water over there, but actually there's no water. This happens due to refraction. So let us say it is very hot. So the land has become very hot. The air close to it is warm and the air higher up is colder. Now, hot air is rarer and cold air is denser. That means in this direction, the refractive index is increasing. Okay. So there's a tree here and there's an observer here. A ray of light can of course go directly, but we are talking about this ray of light. It is going from denser to rarer. So if I take a particular interface, this is the angle of incidence. It will bend away from the normal like this. Angle of refraction is greater. So like that, that bending happens at every single layer and then it turns and then it reaches the eye. And when you extend this ray backward, the image is created here. And likewise, the image of the whole tree is created like this inverted image. And you feel that there is a reflection happening due to water. But when you actually go there, there's no water. So this is actually due to Snell's law in operation, which is refraction. It is not true that this is due to a phenomenon called total internal reflection. It is not due to total internal reflection. It is just refraction that is occurring. So we'll learn about total internal reflection and then you'll see why that is not correct. At this particular point, this is a layer, this is the normal at the point of incidence. If total internal reflection were to happen, then the ray would have gone straight like this, wouldn't have bent. We will talk about that later. Now, one thing I talked about is if there's a coin kept in a glass and some water is poured in the glass, then the coin appears to be shifted up. That is the image of that coin created. So the actual depth below the surface of the water is something, but since the image moves up, the apparent depth is smaller than the real depth. So what is the relationship between that? We are talking of a special case of air and water. The refractive index of air is 1. Let us say refractive index of water is n, absolute refractive index. And the observer is observing an object here located at the point O nearly perpendicularly. Okay, so where is the image formed? One ray I'm taking hits this interface perpendicularly, so there's no bending. It reaches the observer directly. Another ray I'm showing this as a large angle, but actually it is very small because the eye is placed directly above this object. So this one hits here. This is the angle of incidence. It is going from denser to rarer, so it bends away from the normal, and the angle of refraction is more. But both I and R are small because we are talking of a near normal incidence. So the image is created at the point C. The real depth is so much, the apparent depth is so much. So how much is the apparent depth? Now, since both these angles are small, we use the approximation that sine of an angle is equal to the tan of the angle. So sine I upon sine R will be equal to 1 by n. Remember, n1 sine theta 1 equal to n2 sine theta 2. So n1 sine theta 1 is equal to n2 sine theta 2. That is why we have sin I by sin r is equal to 1 by n. That is also tan I by tan r. Now what is tan I? If this is I, this is also I. So tan I is AB upon AO. This is tan I. What is tan R? If this is R, then this is a perpendicular here, so this is parallel to this line, so this is also R. And tan R is AB upon AC. This is tan R. Tan I by tan R is 1 by n, so AB cancels, it is AC by AO. AC is the apparent depth and AO is the real depth. So 1 by n is apparent depth by real depth, or n is real depth by apparent depth. So that is a relationship. Since n is greater than 1, real depth is more than apparent depth, or apparent depth is lower. That's what happens if you go to a swimming pool, you look into the water, you feel it is very shallow, and when you jump into it, suddenly you realize that no, it is not that shallow, it is much deeper than that. Because you're seeing the floor of the swimming pool, whose image is lifted up. Now, this equation is only valid for a near normal incidence, otherwise not. Now we know why the pencil is bent. The image of this point is created here, the image of this point is created here, the image of this point is created here. Therefore, the image of all the part of the pencil that is inside the water is like this, and hence it appears bent. Why you see a slightly different picture is because this water itself is like a cylinder and it is actually a lens. So some other things come into play, but here we are just talking about the bending of the pencil. Now, let's take this question, very interesting question. There's a lake. There's a fish in a lake, okay? So there's a fish in the lake. It is at some depth, we don't even know the depth. But the fish in the lake is moving upwards with a speed of 5 meters per second. There's an observer on the boat, and the boat is just almost vertically above the fish. So the observer is here. So again, that is a near normal incidence. As seen by the observer, what is the speed of the fish? The n of what is 4 by 3? Is it the same as 5 meters per second, or is it more, or is it less? So let us solve this with taking some numbers, okay? Suppose right now it is at a depth of 10 meters, right? Right now it is at a depth of 10 meters. After 1 second, it will be at a depth of 5 meters because its speed is 5 meters per second. So this is the position of the fish initially. This is the position of the fish now. But what was the position of the image of the fish? What the observer sees is not the fish, but the image of the fish. So where was the image of the fish earlier? So if I say O1 and O2 as the positions of the object, then where is the image? Okay, the image is somewhere here, I1, and later on the image is here, I2. So the image moves this distance. So what is the depth of the image? We say n equal to the real depth upon apparent depth. So apparent depth is equal to real depth divided by n. Okay, real depth is 10 and n is 4 by 3. So it is 10 into 3 by 4, that is 5 and 2, 7.5 meters. Okay, so this depth I1 was 7.5 meters. When the object is 5 meters below the surface, then what is apparent depth? The real depth is 5 and the n is 4 by 3. So it is 5 into 3 by 4, that is 15 by 4. So it is 3.75 meters. So it is now 3.75 meters. That is the position of the image. How much has it traveled? 7.5 minus 3.75. That is also 3.75. And all of this happened in 1 second. So therefore, the speed of the image is equal to not 5 meters per second, but 3.75 meters per second. It is lesser than the actual speed. It is lesser than the actual speed. So that's one way of looking at it. Another way is mathematical. So apparent depth is equal to real depth upon n. The rate of change of the apparent depth, that is delta AD by delta T per second, n is a constant, so 1 by n. This is the rate of the change of the real depth with time. The change of real depth with time is nothing but the actual speed of the fish, and the change of apparent depth with time is nothing but the speed of the image. So this is the speed of the image, that is 1 by n, that is 1 by 4 by 3, that is 3 by 4, and this was the real speed, that is 5. So 15 by 4, 3.75 meters per second. This is a better method. This is a faster method. I took this real numbers just to do the calculation, but we don't have to do all of that. Just taking the rate of change gives us the answer. Right? Now, just want to talk about a mirror which is very thick. Then reflection and refraction both will happen. Multiple images will be found. See here, there's an object, a ray comes in here. Now, in any such reflection and refraction, partly it is reflected, partly it is refracted. And if this is made of glass, then we know that 4% of the incident light energy will get reflected and 96% will go in. So first image is created here due to the reflection, and then it comes here, and then there is another reflection by the mirror. So it comes in here. Now when it comes in here, again partly there will be a refraction and partly there will be a reflection. Okay. So most of the incident energy goes this way. So when it entered here, most of the incident energy came down, and after the second event, most of the energy went out. So I2 is the brightest image that is created, but there are other images also created. The second image is the brightest. After this, again, a smaller amount is coming down here, right? So again, an even smaller amount of light energy will go out, and this will be even smaller, right? That is why the second image is the brightest. Now, total internal reflection, and that is the reason for diamond to have that sparkle. Diamond has got a very high refractive index of 2.42. You know that. Now, if a ray is going from denser to rarer, angle of incidence, angle of refraction, it bends away from the normal. All right. Let us increase the angle of incidence. So I increase the angle of incidence, the angle of refraction increases. If I keep doing that, there will be one particular angle when the angle of refraction becomes 90 degrees. It can't go any more than that. So this angle is called critical angle, or theta c. What is the critical angle? It is that angle of incidence when a ray goes from denser to rarer medium, such that the angle of refraction is 90 degrees. That is critical angle. If I increase the angle of incidence any further, then there's going to be no refraction. It is going to get reflected obeying the laws of reflection. This is called total internal reflection. So this is our theta. So if theta is greater than theta c, then total internal reflection occurs. And all of this happens only for denser to rarer medium. And in total internal reflection, there is no refraction. 100% energy is reflected. That is why it is called total internal reflection. Otherwise, also there is a reflection and refraction, but that is not total internal reflection. Now, this theta c is related to the refractive index. If I take this refractive index as n1 of the medium 1, medium 1 is where the ray originates, medium 2 is where the ray goes. Applying Snell's law, n1 sine theta 1 is equal to n2 sine theta 2 for the critical angle. So n1 sine theta c is equal to n2 sine r, that is 90 degrees, right? Therefore, sine theta c is equal to n2 by n1. N2 is less than n1, sine has to be less than 1, right? So this is all right. If medium 2 was air, then sine theta c is simply 1 upon this n1. So quite often we say that sine theta c, sine of the critical angle, is 1 upon n of that particular medium, because then this is an absolute refractive index. But in general, sine theta c will be n2 by n1. Now, if you have a very large refractive index, then you will have a very small critical angle. So if a ray of light enters the diamond through refraction, the way it is cut is very important. So it will go and hit various surfaces within the diamond. And since the critical angle is small, the probability that the incident angle at that particular point is more than the critical angle is larger. The sine theta c is small. That means the ray will undergo many total internal reflections before it finally comes out. So that is one contributing reason for the sparkle of the diamond. And also the polished surface and the way it is cut leads to that reflection itself when it hits. There's partly a refraction, partly a reflection. So that also contributes to the sparkle. And also colors you see, that is called dispersion. That is another thing that occurs. But essentially, the sparkling of the diamond is due to the high refractive index of diamond, which means a very low critical angle. Let's take one question on this. There is a swimming pool of certain depth, and the depth is 4 meters. So there is a bottom of the swimming pool, and the depth is 4 meters. There's a small bulb at the bottom of the swimming pool, and it forms a circular light spot on the surface. What is the radius of this light spot? Take the n of water as 4 by 3 and n of air as 1. So why does it form a radius? Well, this ray goes perpendicularly, no bending. This ray is going to bend away from a normal. This ray is also going to bend away from a normal. So angle of incidence is increasing, you see. This is the angle of incidence. This is the angle of incidence that is increasing. And for a particular angle, the ray goes off like that. And that is a critical angle. This is the critical angle, guys. And if any other ray goes like this, then the angle is more than the critical angle. It won't come out. So from above the swimming pool, you will see a circular spot of light. What is the radius of this? So let me call this height as h, and the radius of the light spot, let me call that as r. Okay. And just to draw a neater diagram, this is how the ray goes. This is r, this is h, and this angle is theta c, and this angle is also theta c. So tan theta c is equal to r upon h. Therefore, r is equal to h tan theta c. Now we know that sine theta c, in this case of going from water to air, is simply 1 upon n of the water, that is 3 by 4. So all that we need is tan theta c. Knowing sine theta c, how do you calculate tan theta c? I'll tell you a simple trick. Just draw a right angle triangle. Call this theta c. Sine theta c is 3 by 4. That means perpendicular divided by hypotenuse. So what is the base then? Root 4 square minus 3 square. Root 16 minus 9. Root 7. Therefore, tan theta c is perpendicular divided by the base. Hence, r is equal to h tan theta c. That means 4 into tan theta c meters. That is the answer. So we end the session here, and in the next session we'll start discussing refraction through curved surfaces, namely refraction through lenses.